So in this video, guys, we're going to look at one of the classical, I call it a classic really for me. I love this theorem really. It's very nice and you'll probably see why Mr. G loves this theorem. It has got three forms. So I'll look at this as theorem 2. Now, what this theorem says is that an angle at the center of a circle equals twice an angle at the circumference subtended by the same arc. And this is important. To say the same arc is really, really important. Now let us look at this in the diagram. Here is an arc. We have arc BC. We also have arc BD, by the way, and we also have arc DC or CD. Let's go down. There were three arcs. These are radii, by the way. That's a radius AB, and that's a radius. So we know the radius is always the same, right? So are equivalent. That's what you can think about. Now, this arc subtends angle A. In fact, it subtends this angle here that I'm circling. Okay. Now, if you want to understand what subtend means, you can think of holding. So meaning this thing here, this arc is holding this angle. Remember, an angle is formed by two lines and a vertex or a point. So here is a point, here is one line, here is one line. This arc is holding one point of the one line and another point of the one line. Okay, so this angle is enclosed within this arc. So we say this arc subtends that angle. But this arc also subtends another angle D, that angle there. I hope you can see that. So we can see this arc subtends actually two angles at this point. Now what this theorem is saying that actually this angle, if I were to say this is A1, it is saying that A1, angle A1, should actually be twice angle D. That's what it is saying. You will see, we will have fun and prove this later. For now, just watch and learn. Remember, I said we are studying lines inside a circle. And here we've got how many lines? 1, 2, 3, 4 lines. And we've got a shape. Actually, we can refer to this thing as a quadrilateral. Okay. And of course, in this case, it's another special quadrilateral. As a matter of fact, we've got names for this quadrilateral. Okay. And of course, in this case, this one, we call it a concave quadrilateral. Okay. Mostly what you guys know is what is referred to as convex quadrilateral, your square, your rectangle, your trapezium, your kite, etc. Those are your convex quadrilateral. When a quadrilateral has one side in which edges meet like this, it is a concave. Okay, so now the interesting thing here, as I said, is that this angle is twice that. I want us to quickly do that. All right, let's see if this is true. I'm going to use my measuring tool, of course, again, and measure this angle. Okay, let's see what we get here. This angle is 88.41 degrees. I hope you can see that. Let me just bring it out a little bit. There it is. Now, what is the half of 88.41, or whichever way you like it? So the half is 44.2. So we expect D to be actually 44.2 degrees. So let's go ahead and measure this angle. We're going to measure this angle and see if we get the desired result. Bravo, excellent. There is the desired result. And so we can see the cool thing about this theorem. It works, guys. Okay, so again, it comes from observation. Now, I'm gonna do what examiners usually try and do. They try and mess around with your head. So I'm going to move this stuff here and I want you to watch. Okay. Now, notice that as I move my, especially this point B, the size of the circle decreases or changes. So don't expect the same measurement as the ones we got, but the relationship should be retained. So check this. Now, if I do this, most students then again start struggling and say, no, but this theorem is not the way we know it, and say is not fair or what. No, guess what, guys? Here is still the arc. Here is your arc. And what you need to notice is that this arc still subtends angle A here and also subtends angle D there, as you can see. The arms of this angle are held by this arc, and the arms of this angle are also held by the same arc. That's another thing that you need to realize. And we can see the theorem. If we were going to say 41.56 times 2, we're going to definitely get 83.12. So the theorem is still true. So you can see what you needed to realize is that, oh, in this case, actually, this angle is twice this angle there. Now, let me talk about the third possible form that they can give you to trick you also. And I know after watching this video, they will never ever trick you again, right? So let's take this back. Now, what I'm going to do here is I'm going to play a little bit funny, and I'm going to do that. Well, maybe that's too big. And then I'm going to do that. Then again, you'll be like, what on earth is that? Well, guys, what you need to realize here is that things have changed slightly a little bit. In this case now, we are no longer dealing with an acute angle. We're actually dealing with a reflex angle at the same time. Okay? And that's what you need to understand. Let's look at it this way. Which arc have we been dealing with? Okay? Let me take you back a little bit. So let's see. I have arc BC. I hope you can see that, arc BC. So if we move this way and that way, I'm still having the same arc. It's just that the arc is too big right now. So you see, this is the whole arc. You see, the arc is just big. And you can see the bigger the arc it is, the bigger the angle that is there. So this is a reflex angle, okay? Now, we can see the theorem should still work. 238.57 divided by 2. Guess what? We get 119.29. So this thing is still twice that. And you can see also the arms of this angle D are still held by points B and C. The same thing here. Now, it's just that this one, you must read it this way. So here is B, here is C. This is your angle. That's how you are measuring your angle in this case. And this way, I've seen a lot of students getting confused. I just want to say to you, relax, know your story. That's all you have to do. Okay, guys, that's about it from me regarding this angle. We are going to look at another interesting theorem that comes as a result of this theorem that we have just discussed. So stay tuned.